In computer science, heap sort is a comparison-based sorting algorithm. Heap sort can be thought of as an improved selection sort. Like that algorithm, it divides its input into a sorted and an unsorted region, and it iteratively shrinks the unsorted region by extracting the largest element and moving that to the sorted region. The improvement consists of the use of a heap data structure rather than a linear time search to find the maximum. Although somewhat slower in practice on most machines than a well-implemented quicksort, it has the advantage of a more favorable worst-case runtime. Heap sort is an in-place algorithm, but it is not a stable sort. Heap sort was invented by J.W.J. Williams in 1964. This was also the birth of the heap, presented already by Williams as a useful data structure in its own right. In the same year, W. Floyd published an improved version that could sort an array in place, continuing his earlier research into the tree sort algorithm. Overview: the heap sort algorithm can be divided into two parts. In the first step, a heap is built out of the data. The heap is often placed in an array with the layout of a complete binary tree. The complete binary tree maps the binary tree structure into the array indices. Each array index represents a node, the index of the node's parent. Left child branch, or right child branch are simple expressions. For a zero-based array, the root node is stored at index 0. If I is the index of the current node, then I parent equals floor 2, I leaf child equals 2 asterisk I plus 1, I right child equals 2 asterisk I plus 2. In the second step, a sorted array is created by repeatedly removing the largest element from the heap, and inserting it into the array. The heap is updated after each removal to maintain the heap. Once all objects have been removed from the heap, the result is a sorted array. Heap sort can be performed in place. The array can be split into two parts, the sorted array and the heap. The storage of heaps as arrays is diagrammed here. The heap's invariant is preserved after each extraction, so the only cost is that of extraction. Algorithm: the heap sort algorithm involves preparing the list by first turning it into a max heap. The algorithm then repeatedly swaps the first value of the list with the last value, decreasing the range of values considered in the heap operation by 1, and sifting the new first value into its position in the heap. This repeats until the range of considered values is one value in length. The steps are called the build max heap. This builds a heap from a list in O operations. Swap the first element of the list with the final element. Decrease the considered range of the list by 1. Call the sift down unless the considered range of the list is one element. The build max heap in performance. The sift down, and is called n times. Therefore, the performance of this algorithm is O, which evaluates to O. Pseudocode: the following is a simple way to implement the algorithm in pseudocode. Arrays are zero-based and swap is used to exchange two elements of the array. Movement down means from the root towards the leaves, or from lower indices to higher. Note that during the sort, the largest element is at the root of the heap at 0, while at the end of the sort, the largest element is inner end. Procedure: heap sort as input. An unordered array of length count heapify end count 1 while end greater than 0 do swap end 1 sift down. The sorting routine uses two subroutines, heapify and sift down. The former is the common in-place heap construction routine, while the latter is a common subroutine for implementing heapify. Procedure: heapify is start type parent while start 0 do sift down start 1. Procedure: sift down is root start while I leaf child end do child I leaf child swap root if a swap less than a child swap child if child plus 1 end and if swap less than a child plus 1 swap child plus 1 if swap equals root. Return else swap root swap. The heapify procedure can be thought of as building a heap from the bottom up by successively sifting downward to establish the heap property. An alternative version that builds the heap top down and sifts upward may be simpler to understand. This sift-up version can be visualized as starting with an empty heap and successively inserting elements, whereas the sift-down version given above treats the entire input array as a full but broken heap and prepares it starting from the last, non-trivial sub-heap. Also, the sift-down version of Heapify has O-time complexity, while the sift-up version given below has O-time complexity due to its equivalence with inserting each element, one at a time, into an empty heap. This may seem counterintuitive since, at a glance, it is apparent that the former only makes half as many calls to its logarithmic time-sifting function as the latter, i.e., they seem to differ only by a constant factor, which never has an impact on asymptotic analysis. To grasp the intuition behind this difference in complexity, note that the number of swaps that may occur during any one sift-up call increases with the depth of the node on which the call is made. The crux is that there are many more deep nodes than there are shallow nodes in a heap, so that sift-up may have its full logarithmic running time on the approximately linear number of calls made on the nodes at or near the bottom of the heap. On the other hand, the number of swaps that may occur during any one sift-down call decreases as the depth of the node on which the call is made increases. Thus, when the sift-down Heapify begins and is calling sift-down on the bottom and most numerous node layers, each sifting call will incur, at most, a number of swaps equal to the height of the node on which the sifting call is made. The Heapsort algorithm itself has O-time complexity using either version of Heapify. Procedure Heapify is child of the root end equals 1 while end less than count sift-up end equals end plus 1. Procedure sift-up is input. Start represents the limit of how far up the heap to sift. End is the node to sift up. Child equals end while child greater than start parent equals I parent if a parent less than a child then swap child equals parent else return variations. The most important variation to the simple variant is an improvement by Floyd that uses only one comparison in each sift-up run, which must be followed by a sift-down for the original child. The worst-case number of comparisons during the Floyd's heap construction phase of Heapsort is known to be equal to 2n-2s2-e2, where S2 is the sum of all digits of the binary representation of n and E2 is the exponent of 2 in the prime factorization of n. Ternary Heapsort uses a ternary heap instead of a binary heap, that is, each element in the heap has 3 children. It is more complicated to program, but does a constant number of times fewer swap and comparison operations. This is because each step in the shift operation of a ternary heap requires 3 comparisons and 1 swap, whereas in a binary heap 2 comparisons and 1 swap are required. The ternary heap does 2 steps in less time than the binary heap requires for 3 steps, which multiplies the index by a factor of 9 instead of the factor 8 of 3 binary steps. The smooth sort algorithm is a variation of Heapsort developed by Edgar Dijkstra in 1981. Like Heapsort, smooth sort's upper bound is O. The advantage of smooth sort is that it comes closer to O-time if the input is already sorted to some degree, whereas Heapsort averages O regardless of the initial sorted state. Due to its complexity, smooth sort is rarely used. Levkopoulos and Peterson describe a variation of Heapsort based on a Cartesian tree that does not add an element to the heap until smaller values on both sides of it have already been included in the sorted output. As they show, this modification can allow the algorithm to sort more quickly than O for inputs that are already nearly sorted. Bottom-up Heapsort was announced as beating quicksort on arrays of size 16,000. This version of Heapsort keeps the linear time heap building phase, but changes the second phase, as follows. Ordinary Heapsort extracts the top of the heap, at 0, and fills the gap it leaves with the end. Then sifts this latter element down the heap, but this element comes from the lowest level of the heap. meaning it is one of the smallest elements in the heap, so the sift down will likely take many steps to move it back down. Bottom-up heap sort instead finds the element to fill the gap by tracing a path of maximum children down the heap as before, but then sifts that element up the heap, which is likely to take fewer steps. Note: this code uses one-based arrays. Function leaf search is ji while 2 times j n do if 2 times j plus 1 less than end and if 2 times j plus 1 greater than if 2 times j, then j 2 times j plus 1 else j 2 times j return j. The return value of the leaf search is used in a replacement for the sift down routine. Function sift down is j leaf search while I greater than a j do j parent x a j I while j greater than I do swap x a parent. J parent bottom-up heap sort requires only 1.5 n log n plus o comparisons in the worst case and n log n plus o on average. A 2008 re-evaluation of this algorithm showed it to be no faster than ordinary heap sort, though, presumably because modern branch prediction nullifies the cost of the comparisons that bottom-up heap sort manages to avoid. Comparison with other sorts. Heap sort primarily competes with quicksort, another very efficient general-purpose nearly in-place comparison-based sort algorithm. Quicksort is typically somewhat faster due to some factors, but the worst-case running time for quicksort is O, which is unacceptable for large datasets and can be deliberately triggered given enough knowledge of the implementation, creating a security risk. See quicksort for a detailed discussion of this problem and possible solutions. Thus, because of the O upper bound on Heapsort's running time and constant upper bound on its auxiliary storage, embedded systems with real-time constraints or systems concerned with security often use Heapsort. Heapsort also competes with merge sort, which has the same time bounds. Merge sort requires a mega auxiliary space, but Heapsort requires only a constant amount. Heapsort typically runs faster in practice on machines with small or slow data caches, and does not require as much external memory. On the other hand, merge sort has several advantages over Heapsort. Merge sort on arrays has considerably better data cache performance, often outperforming Heapsort on modern desktop computers because merge sort frequently accesses contiguous memory locations. Heapsort references are spread throughout the heap. Heapsort is not a stable sort. Merge sort is stable. Merge sort parallelizes well and can achieve close to linear speedup with a trivial implementation. Heapsort is not an obvious candidate for a parallel algorithm. Merge sort can be adapted to operate on singly linked lists with O extra space. Heapsort can be adapted to operate on doubly linked lists with only O extra space overhead. Merge sort is used in external sorting. Heapsort is not. Locality of reference is the issue. Intrasort is an alternative to Heapsort that combines quicksort and Heapsort to retain advantages of both. Worst case speed of Heapsort and average speed of quicksort. Example: let 6, 5, 3, 1, 8, 7, 2, 4 be the list that we want to sort from the smallest to the largest. 1. Build the heap. 2. Sorting.